Good day, everyone, and welcome to this comprehensive and expanded lecture on gravitational lensing by cosmic strings or primordial black holes, two of the most captivating and exotic possibilities for the nature of dark matter that have captured the imagination of cosmologists and particle physicists alike. As of December 19th, 2025, the observational constraints are both remarkably tight and intriguingly open in certain regimes. The Subaru HSC CAM collaboration has released updated microlensing analyses with deeper imaging data, further restricting the allowed abundance of subsolar primordial black holes. The LIGO Virgo-Cagra Consortium's fourth observing run, O4, has incorporated additional months of data to strengthen upper limits on stochastic gravitational wave backgrounds potentially sourced by PBH binaries or cosmic string loops. Euclid's early data releases are beginning to scour vast galaxy catalogues for the distinctive undistorted double images characteristic of string lensing. And commissioning of the Vera C. Rubin Observatory's legacy survey of space and time is progressing, promising an unprecedented leap in microlensing sensitivity. Over the next 15 minutes, we will methodically explore the theoretical motivations and formation mechanisms for these objects, delve into the rich variety of their gravitational lensing signatures across different mass and tension scales, review the current state of observational searches with emphasis on these fresh 2025 developments, examine connections to grand unified theories, inflationary models, and early universe phase transitions, discuss the remaining viable parameter space, including extended PBH mass functions and low-tension strings, address key detection challenges and potential systematics, and conclude with the transformative prospects offered by upcoming facilities that could either detect these exotics or close the remaining windows for good. Dark matter, inferred to make up approximately 85% of the universe's total matter content from a wide array of cosmological evidence, including the cosmic microwave background power spectrum from Planck and ACT, galaxy cluster dynamics, rotational curves of spiral galaxies, and the large-scale structure mapped by surveys like SDSS and DESI, has proven extraordinarily difficult to identify at the particle level. Decades of dedicated experiments, from underground direct detection efforts searching for weakly interacting massive particles, WIMPs, to collider production at the LHC and axion searches with haloscopes like ADMX, have returned null results or only tentative hints. This persistent non-detection has breathed new life into macroscopic dark matter candidates that behave gravitationally like cold dark matter on galactic and cosmological scales, but originate from high-energy processes in the very early universe. Among these, cosmic strings stand out as linear topological defects, while primordial black holes represent compact overdensities, collapsing directly into black holes without stellar intermediaries. Both are essentially dark gravitational objects capable of lensing light from distant sources, offering a powerful, emission-independent probe that complements particle searches and gravitational wave detection. Let us first consider cosmic strings in detail. These are one-dimensional topological defects that form when a symmetry, typically a U1 gauge or global symmetry, is spontaneously broken in a field theory, trapping vacuum energy in thin, stable, line-like configurations. The energy density is characterized by the tension mu, the mass per unit length, with the key dimensionless parameter being g mu over c to the fourth power, where g is Newton's gravitational constant. In classic grand unified theories, GUTs, that attempt to unify the strong, weak, and electromagnetic forces at energy scales around 10 to the 16th giga-electron-volts, the phase transition naturally produces a network of cosmic strings with Gm on the order of 10 to the -7th to 10 to the -5th, depending on the exact symmetry breaking scale. More modern motivations come from string theory-inspired cosmological models, such as brane inflation or axion-like particle landscapes, where fundamental strings or d-strings from higher dimensions can play similar roles with potentially lower tensions. At formation, a network of long infinite strings spanning the horizon and smaller closed loops is created. The network evolves through self-intercommutations when strings cross, producing loops that oscillate and decay primarily via gravitational radiation, maintaining a scaling regime where the energy density in strings tracks the background radiation or matter density. Primordial black holes, on the other hand, were first rigorously explored by Yakov Zeldovich and Igor Novikov in 1966, and gained prominence through Stephen Hawking's 1971 work on early universe collapse. They form if primordial density perturbations delta Rho over Rho on comoving scales re-entering the horizon during the radiation-dominated era exceed a critical threshold of roughly 0.67, leading to direct gravitational collapse into black holes without the need for stellar evolution. The PBH mass is set by the horizon mass at formation. MPBH approximately m to the horizon, approximately 10 to the power of 5 T over S m, ranging from the Planck mass, evaporating today via Hawking radiation, to supermassive scales if formed near or after QCD transition or equality. Generation mechanisms include sharp peaks in the inflationary power spectrum, on small scales from single-field models with inflection points or blue tilts, spectator or curvaton fields adding isocurvature perturbations, first-order phase transitions producing vacuum bubbles that collapse, or domain wall instabilities. To comprise all dark matter while satisfying constraints, extended mass functions, such as log-normal distributions with width sigma and peak mu, or power law forms from critical collapse, are typically invoked, allowing significant abundance in narrow mass windows evading specific bounds. The gravitational lensing signatures of these objects are diverse and distinctive. For cosmic strings, the spacetime around an infinite straight string is conical with a deficit angle delta equals 8 pi gmu, independent of distance. A background source behind a string appears as two undistorted images separated by angular distance delta theta, approximately delta dLs over DOS, where dLs and DOS are angular diameter distances from lens to source and observer to source. For typical GM approximately 10 to the -7, separations are several arcseconds, and crucially, the images are identical in spectrum and morphology without a visible lensing mass, a smoking gun. Moving strings produce time-variable lensing or step-like magnification jumps as they cross lines of sight. Closed loops induce similar but localized and transient effects. Additionally, long strings moving at relativistic speeds drag over dense wakes behind them, causing weak lensing shear in galaxy shapes or temperature steps in the CMB via the integrated Sachs-Wolf effect. Primordial black holes, being point-like compact objects, lens according to standard point mass geometry. In microlensing, a PBH passing near the line of sight to a background star magnifies its flux achromatically with light curve shape determined by impact parameter and relative velocity. Event duration scales as square root of m from milliseconds for 10 to the minus 16 solar mass PBHs to years for supermassive. Surveys monitor millions of stars in dense fields like the Magellanic Clouds or galactic bulge for these rare events. Strong lensing by cluster mass PBHs would create multiple arcs in distant galaxies. Astrometric microlensing shifts star positions by micro-arc seconds, detectable with Gaia. Femtolensing of gamma-ray bursts produces interference fringes in energy spectra for 10 to the minus 17 to 10 to the minus 14 solar mass PBHs. Nanolensing with X-rays probes even smaller scales. The history of these searches is rich. Bernard Paczynski in 1986 proposed microlensing to detect MACOs, massive compact halo objects, as dark matter. 1990s to 2000s campaigns like MACHO, Eros and OGLE toward the Magellanic Clouds ruled out stellar mass dark matter but found some events attributed to known populations. Cosmic string lensing was hunted in SDSS quasar pairs and Hubble deep fields without success. PBH interest waned until LIGO's 2015 gravitational wave detections revived ideas of PBH binaries for some mergers. The 2020s brought dedicated subsolar microlensing with Kepler and HSC and string-weak lensing in DES/KIDS. Current microlensing constraints are led by Subaru HSC, imaging Andromeda halo stars for short-duration events. The December 2025 HSC update, incorporating multi-year deeper exposures and improved photometry, constrains the PBH dark matter fraction, FER PBH, to less than 10 to the power of minus 3 for masses, 10 to the power of minus 11 to 10 to the power of minus 7 solar masses, and less than 0.05 for 0.1 to 1 solar mass. OGL and Korean Microlensing Telescope Network toward the bulge limit 1 to 30 solar masses. To F8 PBH 0.1, no excess events have been confirmed as PBH, excluding monochromatic distributions as all dark matter over a vast range. For cosmic strings, strong lensing searches in JWST deep fields and Euclid's early wide area catalogues find no undistorted double galaxy pairs, limiting GM less than 10 to the power of -9 from billions of sources. Weak lensing analyses in DES Year 6 and KIDS 1000 data, updated in 2025, show no evidence for string wakes in galaxy shear catalogues, constraining GME less than 10 to the -8. CMB temperature discontinuities from the Gott-Kaiser-Stebbins effect in Planck and ACT data-bound GMU less than 10 to the -7. Gravitational waves provide complementary power. LIGO O4's December 2025 non-detection of a stochastic background from PBH binaries excludes FPBH near unity for 0.1 to 10 solar masses. String cusp and kink emissions or loop bursts are similarly bounded, with GM less than 10 to the -15 for certain network models. Nanograv and IPTA pulsar timing arrays probe supermassive PBHs via induced timing residuals or supermassive string loops. Fundamental physics links are profound. High-tension cosmic strings from GUTS would predict observable gravitational waves, but are largely ruled out, favoring lower tension variants from string theory or axion models. PBH formation requires enhanced small-scale primordial power spectrum P of K, greater than 10 to the power of -2, testable via CMB spectral mu distortions from Pixie-like missions, or 21 cm global signal with SKA. Hybrid scenarios where string loops collapse into PBHs combine both. Remaining viable space includes asteroid mass PBHs, 10 to the -17 to 10 to the -12 solar masses, evading microlensing but constrained by Hawking radiation effects on white dwarfs or neutron star capture, planetary mass by femtolensing of GRBs, and low-tension strings gem approximately 10 to the -11 to 10 to the -15 with reduced lensing but potential GW signals. Detection challenges are significant. PBH microlensing events can be mimicked by stellar lenses, requiring parallax or rate distinctions. Extended mass functions fit bounds, but lack unique predictions. String signals are subtle, potentially confused with cosmic variants, foregrounds or systematics in shear maps. Alternative interpretations like wave dark matter or modified gravity compete in explaining observations without exotics. The future is extraordinarily promising. The Vera C. Rubin Observatory's LSST, with commissioning data flowing in 2025 and full operations soon, will monitor billions of stars for microlensing events, achieving sensitivity to FPBH less than 10 to the -4 across wide mass ranges and enabling astrometric detection. Euclid and Nancy Grace Roman Space Telescope deep fields will survey billions of galaxies for string-induced strong lensing pairs. The Square Kilometre Array will map 21 cm hydrogen to probe PBH accretion signatures in the dark ages. Third-generation gravitational wave detectors like Einstein Telescope and Cosmic Explorer will search stochastic backgrounds with orders of magnitude better sensitivity. In conclusion, as of December 19, 2025, gravitational lensing combined with gravitational waves has imposed severe constraints on cosmic strings and primordial black holes as the dominant component of dark matter across most parameter space. Yet intriguing windows persist for extended PBH mass distributions and low-tension strings. These probes offer unique windows into physics at energy scales far beyond accelerators, testing grand unification, inflation, and phase transitions. The coming years with Rubin LSST, Euclid, and advanced GW detectors may finally detect these exotics or close the chapters on macroscopic dark matter. Thank you for joining this lecture. Subscribe and comment your views on PBHs or strings as dark matter. Clear skies.